Most container homes don't fail because of bad design, a weak foundation, or poor welding. They fail because the local climate applies relentless, destructive forces the structure was never meant to tolerate. Steel expands and contracts violently. It traps moisture internally, and it transfers temperature faster and more efficiently than any conventional building system. In the wrong climate, without the right engineering, this turns the container itself into the enemy of the house. In cold regions, the container's steel shell becomes a failure mechanism through two principles: condensation and thermal bridging. The steel frame of the container acts as a massive thermal bridge, a superhighway for cold to travel from the outside directly to the interior structure. Even with insulation between the studs themselves remain cold. Simultaneously, the warm interior air of the home is full of moisture from breathing, cooking, and showering. When this warm, moist air makes contact with the cold steel studs behind the drywall, it hits its dew point. The water vapor condenses into liquid water. This condensation forms inside the structure, not on the surface you can see. It occurs within the insulation cavity, a place with zero airflow. The water accumulates where it cannot evaporate. It soaks into insulation, pools at the bottom of the wall cavity, and begins the slow, silent process of corrosion. This is not a comfort problem or a matter of energy efficiency. It is a long-term structural degradation mechanism that is actively dissolving the home from the inside out. In hot, arid climates like a desert, the failure mechanism is thermal expansion and fatigue. Steel has a high coefficient of thermal expansion. It expands significantly in extreme heat and contracts at night. A 40-foot container can change in length by over half an inch during a daily temperature cycle. Now, consider that this steel shell is attached to other materials: concrete foundations, wood framing, glass windows, all of which expand and contract at different, lower rates. These daily cycles of expansion and contraction introduce constant microscopic movement in every connection point. Welds are stressed, fasteners are loosened, window and door seals are compressed and stretched thousands of times. Over a period of years, this constant movement produces metal fatigue, particularly at the heat-affected zones around welds. It causes sealant failure, leading to dust and water intrusion. And it leads to permanent frame distortion. Doors go out of square, windows lose their alignment. The structure is not collapsing, it is slowly tearing itself apart. In humid and coastal environments, the failure mechanism is hidden corrosion, accelerated by moisture and salt. This is different from surface rust. High ambient humidity allows moisture to migrate through even the most well-installed insulation systems. This water vapor eventually finds the coldest surface available, the inner steel skin of the container, which is often cooled by the air conditioning inside. The vapor condenses on this inner skin, and it remains trapped. The insulation that was meant to protect the container now acts like a sponge, holding this moisture, and in coastal areas, salt-laden air, directly against the steel. This creates an invisible corrosion chamber behind the walls. By the time the evidence of rust, bubbling paint, or weeping stains appears on the exterior, it is a sign of a critical failure. It means the corrosion has already eaten through the full thickness of the steel. The section loss is severe, and the structural integrity is already compromised. A container home survives these climatic attacks only when three specific systems are engineered correctly to counteract these forces. First, a continuous thermal break. This is non-negotiable. The interior conditioned space must be completely decoupled from the exterior steel shell. This is typically achieved with exterior insulation or a continuous layer of interior spray foam insulation that covers everything, including the studs. This eliminates the thermal bridging that causes condensation. Second, a vapor-controlled wall assembly. The insulation system must be designed to manage water vapor. This means a carefully designed assembly with drainage and drying paths, allowing any moisture that does get into the wall cavity to escape. It is not about sealing the wall perfectly, it is about allowing the wall to breathe and dry. Third, a foundation system that prevents differential movement. As the container expands and contracts, the foundation must provide a stable, unified plane that does not introduce its own torsional stresses into the frame. Climate is not an environmental detail. It is a primary structural load that must be accounted for in the engineering. Containers don't fail because they're weak. They fail because the climate applies forces their original design never had to resist. Engineering for the climate is what keeps them alive.